Hey guys, it's Asib, and today we're going to be talking about cryptography and specifically the Caesar cipher, which is the most simple type of cipher there is as far as I'm aware. So the Caesar cipher is a very basic type of cipher where essentially all you're going to do to get from your plain text to your ciphertext is shift each letter by a certain amount in the alphabet. Now, if that's not clear what that means, let me flick to this second slide. If we chose our shift to be a shift of 1, then what that means is we'd shift any letter A we encountered, we'd make it B. And any B we encountered, we'd make it C. Any C, we'd make D, so on until we get to Y. Any Ys, we'd make Zs. And then any Zs we saw, we'd make an A. So we'd roll over. So if I had a shift of 2, my Y would become an A and my Z would become a B. Just to show you that a little more clearly, what you can do is construct a string of your alphabet. So if we start with the regular alphabet, A, B, C, D, blah, 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 we'll construct below that our shifted alphabet, which is, in this case, the alphabet shifted 3 places. So that A will become D, B will become E, C will become F, and so on. And then at the end there you can see that X becomes A, because we've got a shift of 3. Y becomes B, Z becomes C, and that's the end of our key. So you can use this key to help you when you're trying to encrypt a message. So this is how encryption works, and just to further demonstrate, you can see that A has shifted 3 letters across. You can count that if you want. And the same with E. E has been shifted 3 letters across to H. Now to decrypt, all we do is we swap our alphabets. So I'll put my original alphabet below and my shifted alphabet above, and then I just go from the top to the bottom. So whenever I encounter a D, I switch it with an A. And whenever I encounter an E, I switch it with a B. So basically I go 3 letters back in the alphabet. And when I encounter an A, I switch it back to an X, because if I go A, then back 1 is Z, back 2 is Y, and back 3 is X. If my shift was 4, then an A would become a W in decryption. So this is how you decrypt. And it's important that you remember you've got to shift by whatever shift you're using. So if someone sent you a message that's encrypted with a shift of 17, you have to shift by 17 when you decrypt. If you shift by a different number, your message won't make any sense. So just keep that in mind. Now we can represent this encryption system algebraically as a pair of algorithms E and D, which will stand for encryption and decryption. And we have to introduce a little bit of notation here. What we're going to do is we're going to assign the numbers 0 to 25 to the letters A to Z respectively. So we're almost encoding the letters A to Z with numbers 0 to 25. And the reason we're going to do that is because then when we try to encrypt a message, we'll do it mathematically using these 2 equations. So you can see here I've got E subscript n of X, which means the encryption of X with a shift of n is equal to X plus n. So add the shift to the letter. X is the letter in this case, or the whole message. So add the shift to each letter of the message. And then for each letter, mod that by 26. What that does is, say we've got our letter Z, which would have a number value of 25 in this case. Well, if we had a shift of 7, let's say, 25 add 7 is 32. And 32 isn't it's not been mapped to any letter in our notation. So what we have to do is we have to mod it by 26 to get our value back to between 0 and 25. When you mod something by 26, the result is always between 0 and 25. Any number mod 26 is always between 0 and 25. And so going back to our example, if we shift z by 7, we'll end up with 25 add 7 is 32. Mod 26, well, what's the difference between 26 and 32? It's 4, 5, 6. So we'll end up with a numerical value of 6, which would be EFG. That would make it a G. So our Z would be encrypted to a G if our shift was 7. And to decrypt, all we have to do is we subtract the shift and then mod by 26. So if we had an A and our shift was 5, or 0, which is what A is represented as in our notation, 0 subtract 5 is -5. When you mod -5 by 26, what you end up with is 21. Okay? So this is how we represent our encryption and decryption algorithms algebraically. Just to give you a more concrete example, I'll show you the encryption of an actual message. So here, my secret message that I want to send to someone is, this is a secret message. And I want to encrypt it with a shift of 15. So I apply that shift of 15 to each letter in my plain text message, and the result is a ciphertext message that you can see at the bottom. Okay? Now there are some real big problems with the Caesar cipher. Like I said at the beginning, it's the most basic cipher that I know of, and I think it's the most basic cipher that exists. You know, the reason it's called the Caesar cipher is because it was used by the Romans, so it's been around for a very, very long time. And so the problems with the Caesar cipher are that it doesn't provide message integrity, and I'll explain what that means if you don't know what it means in a second. And the other issue is that it's very easy to break the Caesar cipher using only the ciphertext. So if I'm trying to send a message to my friend and someone somehow manages to see that message, not necessarily intercept it, but just get a glance at it while it's being transferred, that person will be able to decrypt that message, decrypt the ciphertext using only the ciphertext. In other words, they don't have any information about the shift or anything like that. Just using the ciphertext, they can decrypt this message very, very easily. So this is a really insecure cipher, in fact. It's not used at all in practice, or at least it shouldn't be. But it's a stepping stone to bigger things and more secure ciphers that we'll see in the future. So this type of attack is called a man-in-the-middle attack. What happens is Alice will try and send her encrypted message to Bob, but an attacker will actually intercept the message. So now the message isn't going to reach Bob at all unless the attacker sends it on. But before he sends it on, what he's going to do is he's going to apply his own shift. He's going to shift it further by 5. So he's going to take each letter of the ciphertext, which as far as we're concerned, and as far as the attacker is concerned, he can't decrypt. But what he's going to do instead is apply his own shift. So he's going to look at the letter I, for example, in the first word, and he's going to shift that onwards by 5, and do the same for all the other letters. Now he's going to send that on to Bob. And what's going to happen is Bob's going to receive this new message, and he's going to try and decrypt with the shift of 15, because that's what Alice told Bob she was going to use to encrypt the message. And when he decrypts it, what he's going to realize is that it doesn't make any sense. And the reason is because the attacker applied his own shift. So once the attacker applied that shift, the overall shift of the message was 20. And when Bob went to decrypt it, he only shifted it back by 15. So the resulting message is actually the original message shifted by 5. But Bob doesn't know that, and so he can't read the message, essentially. So this is what lack of integrity means. And it's a real big issue, basically. And it means that the Caesar cipher is, in practice, pretty useless. Provided the attacker knows what he's doing, he can really screw up the message such that it's unreadable once someone tries to decrypt it. Now, I also said that the cipher is very easy to break. The Caesar cipher is very easy to break, and it's breakable by one of the most simple forms of attack, and that is a brute force attack. So if we're given a ciphertext, or if our attacker receives or eavesdrops a ciphertext, he can just try decrypting that ciphertext with all the shifts 0 through 25 and determine which of the results is the actual plaintext just by looking at it and seeing which of the 26 plaintexts he gets actually makes sense and contain proper English, essentially. And computationally, this is no problem at all to do. Even with a very, very large message, just having to try 26 different shifts is perfectly fine. This is so breakable, it's unbelievable. And again, you really don't want to use this in practice. It's purely, like I said, a stepping stone onto more advanced types of ciphers that we'll see in the future. I should also mention that there are other methods of attack involving frequency analysis, which we'll look into more in later videos. But you don't need those methods to decrypt or to break a Caesar cipher, purely because it's so simple to break it just by brute forcing it in this way. You don't need to consider any sort of frequency analysis. So now let's talk a little bit about how we'd actually implement a Caesar cipher in code, and I'll be using Python to do this. So the first thing we want to consider is how a character is actually represented by a computer. Well, for ASCII encoding, which is probably the most standard encoding that there is, a character is represented by a number between 0 and 255. So there are 256 possible characters, each mapped to one of those numbers. If you go to ASCIItable.com, you can see all of these. Here you can see it starts at 0, all the way down here we get 255. And some of these characters are mapped to actual letters. I can't drag, but oh well. You can see them all here. So we've got the uppercase letters are mapped to the numbers. Here's the decimal value, 65 to 90. And the lowercase are mapped to numbers 97 to 122. So now we know how those characters are actually represented. How do we find out what the number of what the decimal representation of a character is? Well, I'm going to switch to terminal. I'll open up a Python command prompt, and if I type in the character A, we can see it gives me back A. So what I want to do is get back the decimal representation of A, and I'll use the function odd in Python. That will give me the value of 97, and you can see if I flip back to my table here, 97 mapped to A. What about if I try capital A? That should give me 65, and it does. Let's verify 65 is capital A. Okay, so now we know how to convert a character to its decimal representation. Now we can actually start to implement our Caesar cipher code. So I'll open up my my Xcode window, and I already have a file called Caesar.py. Let's type in some random string. So I'll call the string string. I'll say this is my plain text, I'll call it. And now I want to convert all of these characters to their decimal representations. Now before I do that, what I want to say is that you have to consider the offset when you're doing all of this stuff. So you can see that if we start trying to use our encryption and decryption equations that we looked at just a moment ago, where we had the encryption of x with the key n, or the shift n, was x plus n mod 26. Well, if we try and do that, because these characters have an offset, it won't work the way we expect it to. So what we have to do is subtract that offset from every single character we come across, then apply the shift, and then make sure we do some cleanup for rollover and that sort of thing, and then reapply the offset so that we get back to where we want to be in terms of ASCII values. Now, there's one problem with that if we look at this string, and that problem is that here we have a capital T. Well, the capital letters, as we can see here, have an offset of 65, but the lowercase letters have an offset of 97. So there are two ways we can do this. What we can do is we can loop through our string here and check to see if the character we're currently looking at is an uppercase character or a lowercase character, and then based on that information we apply the correct offset. Or we can do what I'm going to do, which will slightly change the encryption, and when it's decrypted it will change what it looks like from the original value, but it's not too much of a change. We're just going to make everything lowercase, and you do that in Python with string.lower. Okay, so now if I printed out all my, well, let's do it. I'll print out my string just so you can trust that this is what's actually happening. I'll run caesar.py. Oops, I've got a Python net. If I run caesar.py, I get, there's none there. Why is that? Oh, I'm not in the right directory. Okay, so now if I do that, we should be good. Oh, we need to assign string to this. Sorry, string equals string.lower. That will do the right thing. Okay, you can see it's made the T lowercase now. So now all these characters will have the same offset. So now what we're going to do is we're going to loop through all of them. Like I said, we'll say for character in string. Well, one thing we want to check is if the character we're currently looking at is a space. So what we'll do to do that is just if character equals and a space, or actually we'll do if it's not equal to that, because if it is equal to a space, no, actually, because what we're gonna do is we'll create a new string to store our shifted value. So I'll call this Cipher equals an empty string, and then what I can do is I can say Cipher plus equals empty string, or I'll do Cipher plus equals character. So if it's a space, we're just going to append our space to the string, or to our ciphertext, so that our ciphertext shows up those spaces as well. What we could do is we could not append anything if it's a space, and that would just sort of concatenate all the words together so that we had this one big word. And that would be slightly harder to decipher because it wouldn't be as obvious that to an attacker that someone had just applied a shift to it and left out doing anything to the spaces. I want to add that the reason I have to do this and I can't just sort of apply some shift is because the space actually has its own ASCII value. It has an ASCII value of 32. Here you can see decimal 32 is a space. So if we applied a shift to that and did all the same stuff that we're going to be doing with the characters, then it would actually change what that space was. It would appear as a different character in the ciphertext. So if we want to maintain our spaces, we have to use some sort of functionality like this. Okay, so now we've got our spaces being put into the ciphertext properly. Let's consider what we'll be doing for each character. So for each character, we said we wanted to get the integer value of that character, or the decimal representation, and we do that by doing odd character. Now we need to subtract the offset. So the offset for all these characters, because we made them all lowercase, is going to be 97. So if we subtract 97 from any character A to Z, what that will do is make the value between 0 and 25, which is what we said we wanted it when we were talking about the equation. Remember, it was always something mod 26, and if you mod by 26, you get a value that is between 0 and 25. So that's why we're going to subtract the A offset from each character. So we'll say integer value minus equals 97. So now we've got our decimal values between 0 and 25. What we now want to do is think about our equation. Our equation was encryption of x with a shift of n is x plus n. So let's add a shift to our integer value for each character. I'm just going to use the shift of 5, let's say. Seems good. Now, our equation wasn't just x plus n, it was x plus n mod 26. So now I'm going to mod every single character value by 26. You do that with the mod equals. That means that if any of our characters had an integer value or a decimal representation of, let's say 23, and we apply a shift to them, that would make the decimal value 28, which is greater than 25, and 25 is our maximum value. So by modding it, we again bring it back to that range of 0 to 25. Okay, so now that we've got that, our value is shifted and it's between 0 and 25. What we need to then do is go back and add the shift, or sorry, add the offset. So here we subtracted the offset to get to between 0 and 25. Now we'll add the offset to get between 97, and 122. That's what this is doing. Okay, now that's all great. The only thing we need to do now is convert back to an actual character, because at the moment integer value is just a number. And to convert back to a character, you just use the character function and give it an integer. Okay, so that's great. All we need to do is just append this to our Cipher string. So I'll say Cipher plus equals the character value. And if all is well, which it should be, this should work perfectly to encrypt our string. So let's try and run it again. I'll clear and run it. Name character. I might have got that wrong. I think it's CHR, like that. Sorry, the function is CHR, not CHAR. Let's try that again. And there you go. You can see that we've encrypted our plain text, which is this is my plain text, to this value, which is shifted by 5. Now, if we want to decrypt this, all we need to do is change this plus equals to a minus equals. So I'm going to copy this encryption, and I'll set my string here. I'll reset it to be that encryption, and then this print here should spit out the not the cipher, but the decrypted cipher. So let's run that again, and you can see we got exactly that. This is my plain text. And as I said, that the only difference would be that we took away any capitals in the original string. So the decryption will all be lowercase. So if you want to maintain capital letters, what you need to do is what I said earlier, where you check each character, you check whether it's an uppercase or a lowercase, and then you apply the correct offset given that information.